Good evening, all. Today we are going to start the next phase of computer architecture, that is ISA implementation. In this implementation, we are going to talk what is the structure of instruction and how those instructions are implemented on processor and how they are executed in step-by-step process. And this lecture will continue up to 1 hour, and after that, if you have any questions, you can ask me the questions in the chat box, and I'll try to answer in the last 15 minutes of the lecture. So first, in the implementation of the instruction, as we know that if there is a program, the program is a set of instructions. The program is set of instructions. So how those instructions are executed? This program is treated as a data. The data is given as an input to the sequence of arithmetic and logic functions, that is your ALU. And then, after performing the arithmetic sequence of arithmetic and logic operations, then it gives the result. So what is there inside then? The program is a sequence of instructions. The program is sequence of instructions. Those instructions may be your arithmetic instructions, as every time we are talking about these arithmetic instructions, like your plus, minus, your division, your multiplication, or your logical instructions, those instructions like your and, or, and so and so. Then control instructions. In control instructions, you find the jump instructions or your branch instructions. And then you'll find the storage instructions. So there you can find store or your load instructions. So any kind of instructions. So we say that program is a sequence of instructions. So these instructions will be given to your sequence of arithmetic and logic unit. We call that as your functional unit. So this functional unit, the functions of your control units are, for each operation a unique code is provided that we call your opcode. So those codes may be like addition or move instructions or your subtraction or your division instructions, anything. And the hardware segment accepts the code and issues the control signals. So in this sequence of instruction, the instruction codes will be given as an input to your instruction interpreter. So this instruction interpreter will interpret whether they are the arithmetic operations or logic operations or control operations or your storage operations. And based on that, this interpreter gives the control signals to the ALU. Then the ALU will performs based on ALU will perform the operation. So to perform the operation, you need to provide the operands, that is data. So this data will go and store in the general purpose registers, and from it will supply to our arithmetic and logic units, and ultimately we'll get the results. So these results will go and store either in the register or in the memory or in the cache memory that we observed in the previous classes when we talked about the addressing modes. So then in this, how these instructions are going to be executed, the instruction execution in the stages. The instruction will execute in stages. We'll discuss these stages. So when implementing the instruction set architecture, we typically partition the execution of instructions into stages and implement each stage with the transistors separately. So as we said, if we have an instruction, that instruction we are having the opcode as well as the data, that data is your operand, then it will be separated, and every time it is going to be separated and every part of this instruction is executed. So how and why this, the separation is required, or the different stages are required, or partition the execution means many instructions share the common steps in the executions. Common steps in the execution. That's the first point. That's the reason the instructions are partitioned. Second, therefore, they can share the common functional units. When they are, the instructions share the common steps, they use the common functional units to execute them. So break down these instructions into stages with well-defined execution times. We call these CPU cycles. We are going to talk about that. So every instruction will be divided, partitioned, and every part of the instruction is executed separately because they may use the common steps in that. And that makes the well-defined execution times makes instruction scheduling and the management in the easier way. And another, the important part why the instructions are partitioned means they divide and conquer. They divide and execute it separately and then conquer at the time of a result. So, or we say that another divide and conquer are the abstraction or simplified the designing process of the instruction execution part. So let us see how it happens or how the instructions are executed. So in a different stage. As we know, if we have any instructions, those instructions, suppose if I have the instruction like, add R1 and R2 and store the result in R1. Suppose if you are following the ATT or the other architectural part, add R1 and your R2 or R3, then this entire instruction is going to store in the memory. So this memory is used to store instructions as well as the data also. And these instructions are executed by the functional units. So functional units are in the CPU, central processing unit. In central processing unit, what happens? The instructions will be given to your the control unit. Okay, so for those instructions, control unit go and fetch the instruction from the memory. When they are fetching the instruction from the memory, that is in terms of your data, that goes and stored in the program counter, and then it will be decoded in the instruction register, and from the instruction register it is supplied to the functional unit. Instruction is supplied to functional unit, like from the here, if it is stored like add R1, R2 and R3, it will be fetched, and the address of this, suppose 1002, that will be fetched and stored in program counter. Then this entire instruction will go and store in the instruction register. From the instruction register, the instruction is decoded, that is add is given to your functional unit, and whatever the registers are used, their registers will be, the data will be stored in the registers, and from the register, this functional unit will fetch the data from this instruction register and executes. And once it is executed, the result will go on store either in the register, and from the register, if it is go and store in the memory, then the databases are used to carry that one. So this is generally the top level view of execution of your instruction execution stages. So remember, in instruction execution, the main part is it is having the memory, program counter which holds the address of the next instruction, and instruction register which holds the instruction part, and functional units are used to execute these stages, and registers are used to hold the data. So let us see one by one what are the different stages of the instruction execution. Means there are 5 stages. We call the first stage is instruction fetch. So in this instruction fetch, it fetch from the memory. Second, the instruction decoder, we call ID. The instruction will be decoded, means the instruction is separated and the data is separated, that is instruction partition will be done. And third, it will go for the execution part. It will go for the execution. Once decoded, it goes to execution. Once the instruction executed, then the memory will be allotted for storage purpose. The memory will be allotted for storage purpose, memory. And once memory is allotted, then it gives the write back. The results will be write back into your memory itself. So these are the 5 stages one needs to remember. First, the instruction fetch, then instruction will be decoded, then those instructions are executed, then the memory will be allotted after the execution, and once memory is allocated, the operand and the data will go and store. So that is write back operation will be take place. So in the instruction fetching, it can cover all the instruction. It may be your addition, arithmetic instructions, your logical instructions, your control instruction, or storage instructions. So those will be fetched from the memory. And when it comes to instruction decode part, in instruction decode, it decodes the operation part, or it partitions the instruction to operation and the data part, operation and the data part. And once it is divided, then the data part will go and store in the register. So that is register fetching to according to one. And once it is done, then it goes to execution stage. So in the execution stage, it is going to execute either arithmetic and logical operations, or the memory operations, load and store, or your control operations. So for arithmetic and logic operations, after execution, it goes and back into the memory, right back into the memory. But when it is going to executing the memory operations and the control operations, during the execution, it calculates the effective address. From the effective address, it identifies in which memory the operand is there. So that memory access will be done. The operand will be accessed, and the execution will done, and the result go back and stored in the associated memory. Similarly, in control operations also, it will calculate the effective address, and then it finds branch is executed completely or not. So these are 5 stages. I repeat again: the first stage is instruction fetching, second is instruction decoding, third stage is your execution part, fourth one is memory assignment, and fifth one is your write back. So these are the 5 stages of your instruction execution. So in generally, in the instruction cycle, whatever instruction is given, it is divided into 2 parts: fetching and the execute part. So when it starts, it go for the fetching instruction. So when it is fetching, there are 2 parts in fetching and your execution side. In fetching, it fetch the next instruction. Okay. When it starts, initially no instruction is there, so the first instruction will be fetched, and that will be stored in a specific, the special purpose register. That happens in the fetch cycle. In the execution cycle, the decoding will be done, and every individual instruction will be executed, and this process continued until all the instructions are complete. So what is the instruction cycle means? Instruction cycle is defined as fetch cycle and the execution cycle. So what are these cycles that we discuss? Okay. So here in the fetch cycle, what happens? The first part is fetch cycle. In the fetch cycle, what happens here? So as we saw in the previous diagram, there is in the CPU. In CPU, you are having the special purpose register program counter. This program counter holds the address of next instruction to fetch from the memory. So then another component is your processor. So this processor fetches the instruction from the memory location, which is pointed by the program counter. And then once it is fetched and stores in the instruction register, then your program counter will auto increment. So that is PC is equal to PC plus 1 unless to hold otherwise, because if it is a loop, then same address will be continued. If it is not, then next instruction will be fetched, and the instructions will be loaded into the instruction register, and then the processor interprets the instruction and performs accordingly. The execution starts. So in the execution cycle, what is there? In the execution cycle, you will find the processor memory, processor input output, your data processing, and your control. So what is processor memory? The processor try to transfer the data between your central processing unit and the main memory. So that is, when decoding it, the memory should be allocated for the data. That means your operands, right? And sometimes if the data is not available in the memory, then processor will try to get the data from the input output devices. So input devices and gives the result to the output devices. That is data transfer between CPU and input output module. Then the data processing. Once the data is available, then the data is given to your arithmetic and logic unit that will perform the actual operation. So some arithmetic and logic operations will be performed on the given data. So in the previous instruction fetch, if it is decoded, there are some control signals. Then the alteration of sequence of operations will be done. Example like your jump instruction and those. So the combination of all the above is called as your execution cycle. So let us see in this execution cycle what exactly happens. If the instruction or the elements of your instruction, see if it is a 16-bit instruction, and in the 16-bit instruction, if it is predefined rule as first 4 bits are used for your opcode and the second 6 bits are used for your operand 1, third 6 bits are used for your operand 2, then the instruction is partitioned in this form: operation code, and in the operands will be stored in a separate location. That is happens in the first phase of our execution. We call it as your instruction decoding. First one is opcode, or we write this the operation code or opcode. So do this operation in this execution cycle. For this operation, source operand reference is required. So provide this value to the operation, to this value, and the result operand reference that will be used to put the answer back into this result. So this is the accumulator addressing mode part or accumulator style part. So see, for example, what are the opcodes generally we find in this decoding part, right? So what are the operands? Suppose if we are having the arithmetic operations, the arithmetic operations. So in the arithmetic operations, you will find the addition, subtraction, division, your multiplication, right? So these operations, okay, we write the addition, subtraction, multiplication, division, and this. The mnemonics which are used for the instruction purpose are add, sub, and multiplication. Then the operation code consists of this: add, sub, multiplication. And in this, the mnemonic form, they will give the address also. They will give the code also. That suppose for addition, if number 1 identity is given, it can be written as your 0, 1. If they use it to 4 bits, means it can be given as your 0, 0, 1. For subtraction, it will be given as 0, 1, 0. For the division, it may be given as your 0, 1, 1. Or for multiplication, it may be given as 1, 0, 0. So that is the code which is used, opcode which is used with the 4 bits. If it is 2 bits, then they can be written as your 0, 1, 1, 0, 1, 1, or 1, 1. The 3 instructions will be taken for 0, 0, and that one. So it will be changed based on how many bits we are using. So in this case, let us example how it happens in the execution cycle. In the execution cycle, suppose if we have the instruction like the add instruction for the destination is R0, your first operand is R4, and second operand is R11. You can see these registers are taken from your register 5, and they are identified with the add number here. Okay, so then for addition, if the instruction code opcode is given, if 3 bits are used, okay, 3 bits are used for your opcode and 2 bits are used for your references or operands. Suppose 2 bits are used. So then the total, it becomes the 9-bit instruction. In the 9-bit instruction, 3 bits are for your opcode, 2 bits are for your operands, right? So then the code is given that for addition, if it is the first one in the arithmetical logic, the instruction set, then it is given as 001. And for R1 register, the binary representation is, it is identified with 1, so it is written as 01. For R2 register, 10. For R3 register, 11. So the total code in terms of binary, the instruction design is this one. For this, for execution purpose, this mnemonics or this what you call instruction set will be written in the binary form. As when we talk about this computer arithmetic, we talk about this instruction encoding or binary encoding. But here it complete form can be written as 001, the opcode. First operand is your 01, second operand is 10, third operand is 11. So this is a instruction code, the instruction. So this instruction will go and store in the memory. It go and store in the memory. So to execute this one, this instruction will be fetched from the memory and store in the instruction, fetched from the memory and store in the instruction register. Instruction register, that is 001, 0, 10 and 11. So while this is fetching from the memory and storing in instruction register, first the program counter will go and store the first, what is the address of this one is stored, that comes into your PC counter. From the PC counter, it identifies the location and that instruction is fetched and stored into the instruction register. So how it happens, let us see in this example. Okay, in the our instruction design is addition of 2 registers, addition of this instruction, suppose. Okay, addition of the component or the operands of your R2 and R3 and store the result in R1. So first 3 bits are representing the operation code. Next 2 bits are representing the destination, that is 01. Next 2 bits are representing for first operand. Next 2 bits are representing for the second operand. Okay, so then this entire instruction goes and store in the memory. In the memory, you can find it is in the form of zeros and 1. In zeros and 1, and it is stored at the address, suppose at 2, index 2. Okay, so then what happens? Then this instruction should be fetched from this memory and take it into your central processing unit to perform. So in central processing unit, we are having the program counter and instruction register. Instruction register holds this instruction. Program counter holds the address of this instruction. And once it is available, the fetching phase is over. In the decoding phase, in the execution phase, this instruction will be partitioned. Okay, and that will go and the instructions supplied to your functional unit, and your operands will be taken from your register file and the happen. So let us see. This is the address as said. So if you see in this case, in the first fetching phase, it goes and check the address of the memory. So that address is 2. So that comes and stored in the program counter. Once it is stored, then the program counter will be incremented after execution of this instruction, that is PC plus 1, to execute the next instruction. So initially here program counter doesn't have any address. So first instruction, to store the first instruction, it will hold the first address of the first instruction, and address of the first instruction will be stored, and then the whatever address is there inside the PC, from that address whatever instruction is there, that instruction will be fetched and stored into your instruction register. So fetching phase is over. So now this instruction should be decoded, the second stage of your instruction execution. So this execution cycle. So in the second phase, when the instruction is executed, so that is decoding phase is going on for the first instruction, and at the same time when it is installed, loaded in the instruction register, your program counter will auto increment. So from 2 it goes to the next address until it gives a specified address. So the next address of the next instruction will be stored in PC, and then what happens inside the CPU. So let us see now in the execution cycle, the operand is stored in the R2 register because it's going to perform the operand which is there in R2 and operand which is there in R3. So from this the register file, these registers are holding the operands. So those operands are available in R2 register and R3 register. So decoding is happened now. And from the instruction, this instruction code is decoded. Next, to perform this operation, so operands are also identified. To perform this operation, addition operation, the functional unit, the arithmetic and logic unit, takes the first source from your R2, second source from your R3, given to your ALU, arithmetic and logic unit. ALU performs this operation, and the result of ALU will go and store in the register. So why? Because we are following the method that register to register addressing mode, register to register instruction. So the operands comes from the register to your ALU, and the operation will be performed and result will go and store in the register itself. So that operation, so the operand of your R2 and operand your R3 supply to your ALU, and result goes and store in the R1 register, that is R1 register, which are available in the register file. So this entire part is your register file. So once this is executed, once this operation is this instruction is executed, right? So then it goes and check, the control signal goes and check in the program counter. The program counter, it is saying 3. That means it start going to execute the next instruction. So here you can see first it is decoded. Once decoded, then the memory is allocated where the operands are. So when it goes to execution, once execution is happened, then the result must goes and store. So the memory is allocated R2. Memory allocation R2 is allocated, right? In this case, so when it is allocated, then the write back operation will take place in the write back in the arithmetic and logic unit. Once it is executed, the write back operation will take place. That write back operation goes and write into the memory, right? So let us see. So first instruction is successfully executed, then your instruction register becomes free now, so that will be used to store the next instruction 3. That will be used to store the next instruction 3. Okay. If instruction 3 in that location we don't have any instruction, so the program counter will go and auto check the next instruction. So this is what happened inside the CPU. So the execution of a simple program, here you can see the following programs were loaded in memory starting from the memory location 0. The memory locations are given 0, 1, 2, and 3. Okay, consider this program. In this program, the instructions are stored at first instruction, the load instruction stored at location 0, read instruction stored at location 1, subtraction instruction stored at location 10, and store instruction stored at location 11 in the main memory. And they are having the operands also. The source and destination. Okay. So here is the R2 and R1, the R2 and ML1. So they becomes the source and the destination itself. R2 is source as well as the destination. It is like memory. So what is happening here? We are using the ML4. That is the operand is available at memory location 4. Memory location 4, and the operand in that memory location is 5. So that is the binary form of that operand is 101. In the read instruction, the destination is R3, that is available in the register file itself. So the operand is input 14. Take this input from the input output device input output device of your 14th instruction, and the value is suppose 7. And for subtraction instruction, it says that R1, R2, R3, they are available in the register file, but what they are holding here, it is performing the operation that R3 minus your R2, R3 minus your R2, okay, and the result is stored into your R1. So in the R2, the result is it is taking 5. From R3, it is taking 7. So the result is 7 minus 5. That is ALU operation performed, and the result is 2. So for this 2, R1 is allocated, the memory is assigned, and this the 2 will be right back into R1. Similarly, for the instruction store instruction, okay, the operand which is available at the memory location 5 will go and store in the associate the memory which is assigned to it at R1. Okay, so that the R1 will go and store, it is the write back. So like this operation, ALU operation part, this is the memory operation. So see here, in this case, the example of this program in the memory, by considering this previous program, okay, is the instruction starts loading from 0 and continue 1. So let us see how it is happening in the memory allocation. So we have seen the execution, fetch code, fetching the code, then decoding, then the execution we have seen in the previous case here, and then comes to the memory allocation. Okay, in memory allocation and store. Now see, in the main memory, in this main memory, you can see the main memory or the memory allocation part. The first instruction is your load the content of HTML4 into your R2. So the binary code which is given to it in the 3-bit code is given 0, 1, 0, 0, 1, 0 suppose, and for R2 with 2 it is represented as your 1, 0. At memory location 4 it is represented as 0, 1, 4, 1, 0, 0, so that is 4. So total instruction code it is become as your 0, 1, 0, 1, 0, that is R2, and 0, 1, 0, 0 is. So this is going to store as per the instruction. Here it goes and store in the 0 location in the main memory. So in the 0th index, it is represented with 4 bits as 0th location. In the 0th location, this instruction, this entire instruction is going to store. So that is 0, 1, 0, 1. So this is opcode, your R2, and your memory location 4. Similarly, the next instruction is read instruction. For read instruction, the opcode is given 100, and for R3 it is 11. And for this, the input that takes 4, suppose input 1, which is taking the 4th input output device, then it is written as this one. So it will store in the 2nd location, as it is mentioned in the case this location in the main memory. So similarly for subtraction, if it is given the opcode 000, and for R1 it is 01, R3 is 11, R2 is 10. Okay, this is but we are going to talk about this detail in the data computer arithmetic, where how these are encoded. Okay, and for store instruction it is 011, for example, and for R1 01, and for memory location this one. So they are stored in 4 locations now. Location 4. Okay. So after that, at the 5th location we don't care about. At the 4th location it may have some other operations. Okay. So and after that, some other instructions may also available in the content. They are occupying some other locations. So we are concerned about the first 3 part. Okay. 4th location is already occupied with some other instruction, but for our program, these memories are allocated, so the instructions are stored in this memory location. So what happens next in the execution? Suppose if you have the operation that load the operand which is there in your memory location 5 into your R2. So it is based on its encoded. It is for load it is 010, and for R2 it is 10, and for memory location that is suppose it is 0114. Then how this execution happens, let us see. First, the instruction program counter holds the first instruction from the memory, that is 0. Then the instruction is fetched. So this is the instruction which is given to us. So that will be fetched. Instruction. Okay. So this instruction is stored. That is at location 0. Program counter stores 0. Then instruction will be fetched from the memory, and that will store in the instruction register, and then it is decoding, it is giving the instruction, that load instruction. Okay, for that it requires the operands. So for operands it must provide the memory location. So what is that? The first operand comes from the R2. So the value of your R2 will be the value of R2 is holding the value 5. Then the second operand for this load instruction, so that should be given. For that, once it is allocated, the location 5 is allocated to this. I mean the at that location, whatever the operand is there, that operand is given to the instruction ALU. So when it is decoded and first one is executed, program counter will be incremented, and then it goes and increment the program counter from 0 to 1. Then it try to fetch the instruction from the memory. That is the second instruction. Second instruction is your read instruction. Read instruction format is 10011, and that. So it must be fetch and store. Fetch and store in the instruction register. So that will be fetch and store, and then the decoding part will be happen. In the decoding, it is the read one. So read operation should be performed. For that read operation, one operand is from your R3, another one is from your what you call the R2, sorry, the input one. So from R3, the operand will be fetched from this R3, whatever operand is available in this R3 register, and then the result, the program counter goes and execute the next instruction. So that is at memory location 2. So at memory location 2, the subtraction instruction is there. So in the subtraction instruction and the operands, which is binary encoded, the instruction is 000, 01, 111, and 0. So that will be fetched and stored in the instruction register, load in the instruction register. Now this instruction, from this instruction register, decoding will happen. So that decoding is your subtraction. So subtraction will be given, and in the execution phase for this subtraction, it must provide two operands. One is the content of your R3 and content of your R2. So R3 content and R2 content is given. Then it performs the subtraction operation, and then the memory should be allocated for this result. So that allocated memory is your R1, and whatever result is there, the result goes and stored in the memory, that is write back operation. And then the program counter, once this operation is over, write back is over, the program counter goes and increase to load the next instruction. So that is second instruction is executed. So third instruction. So then in the third instruction from the memory, it is taking the third instruction is store 1. The instruction format is 0111. So it must fetch from the memory and store in the instruction register, and that from that instruction register it gives the store operation, that instruction. For that it requires the operands. Operands are the content of your R1 and content of your memory location 5. So that will go, and then it goes to here the result is store the content of your R1 into the memory location 5. So it is single instruction. Then it goes to the next instruction 4. In the fourth instruction, it is allotting the memory location 5. In the memory location 5, the result will go and store. So with this, all the instructions of the program is executed, then it start going to execute the next instruction of the program. Okay, so there you can see before program execution, we have seen the instructions are loaded in this memory location. After the execution of the program, the memory initially, the fifth memory is allocated at store at memory location 5. ML5 is allocated in this memory location. Whatever the result of your R1 is there, that R1 will be go and store here, that is write back. So after execution of the program, it will go and store the result of your R1 in this memory location. We call this write back. So these are the phases of the execution stages of your instruction. What is that? First one is instruction fetch. So in the instruction fetch, the instructions are fetched like your load, then your read, then your subtraction, then your store. Instructions are fetched, and then in the execution part, execution cycle, their operands are also supplied to your functional units, and the write back operation happens at the end of this one. So what is happening in the instruction decoding? Let me just summarize again. The instruction decoding and register fetching happens in the instruction. So that is, it decides what type of instructions we have, whether the operations are ALU or branch or memory. So we have seen, the subtraction instruction is decided. Then we also seen the store instruction, that is our store or load instruction, that is the memory instructions. So then it decodes the opcode. That is what we observed. The opcodes are decoded in the previous example we have seen. Then it gets the operands from the register files. That it may be from in our example, the register we use R1, R2, and R3. That is, get operands from the registers. So that is part of the instruction that determines where the operands are from. For example, like this R1 register and R2 register, like the source register value will be stored into your accumulator in A, and another register stored into your B. So that is what we observe, like C is equal to A plus B, means we have seen that R1 holds A, R2 holds B, and R3 holds suppose C. Then it is written as R3 is equal to your R1 plus your R2, like that. So it holds the address. So operands will be get from the register files, and then it performs the performance affected by the regularity of your instruction format and instruction length. In our previous case, we used 9 bits instruction. So as we said, some may be having the 12 bits instructions, some may have the 8 bits instruction. So if bits are changed, means length are changed, it is your complex instruction set computer sys computer instructions. So then suppose if you are going to execute memory operations, what we need to do, if you see this example, here we see, if ALU operations are happen, means you are simply instruction is fetched and instruction is decoded, then they start executing and result is stored in the write back. But if you have the instructions like memory operations or control operations, first they are going to calculate the effective addresses. Just a second. Yes. So in the to execute in the execution cycle of the instruction with the memory operations, so with this memory operations, then what happens? They calculate the memory address for the data using arithmetic and logic unit first. The memory address will be calculated. So as we have seen that if you have the instruction like suppose if arrays are there, suppose the arrays are there, we have seen some elements are there in the arrays, then the instruction will be written like this: R1 is equal to R2 plus your R3. So for that, first R3 is calculating the address, effective address, the address of your element, and that is stored in this location, right? So that is the memory address will be calculated first. So addressing modes here, the direct how to compute the effective memory address. So for example, see this, the following instruction, move instruction. Suppose in this move instruction, move the value of your location content at the location R2 plus 100. So what it means, R2 is the base address and 100 is the displacement address part. Okay, sorry. Is it visible, right? Fine. Okay. Thank you. Thank you for letting me know. Yeah. Okay. Yeah. So as we see some of the instructions which are associated with the memories, like if you have the instruction like move instruction, move content of your the stack or your array, that is R2 plus your 100. So this is the displacement addressing mode, right? So here is the base address, this one is the displacement. So this will be calculated first. So where R2 holds the base address, and then it is adding to the displacement. So from that stack, it will hold the, suppose it starts at 0, 0, 1000 location in the stack memory, and if the element is at the 100th the displacement is suppose 100, then at the 100th location it will be the suppose some 5, like that element. So for this kind of instruction, what you need to do if memory operations are happening means, first the memory address will be calculated using your ALU. So the effective address is computed by summing the value of your R2 plus and 100, this one first. So what happens, this move is the instruction or opcode, R2 is your destination, R1 is your source register, but the base address is consist, and 100 is your immediate one, that is the displacement value part. Okay. So now see, some of the ALU operations which we already discussed. I just want to recall this. This ALU operations performs the computations, and it uses the register to register the instruction set syntax. So where the operands will register to registers, it may use the special purpose register called the accumulator. In the accumulator, the operands will be given. One operand comes from your accumulator, another comes from your register memory register, and it performs the operation, and the output will go and store in the ALU register itself, that is A itself. Or if it is following the register to immediate one, then one operand comes from the accumulator, one comes directly from your direct value will be there, and the operation will be performed and result will store in this. So in this ALU, it may be your plus, minus, division, multiplication, or your AND operation, OR operation, or your exclusive OR operation, or anything. So here also it is the same one for immediate also. But here the operand is in the register, but here the operand is immediate value, that is it may be 4, 5, 6, anything. So that happens in the execution of your ALU. Whereas in memory access, as we said, first the ALU calculates the address, that is R2 is going to, in the previous example we consider R2 is holding the base address of the element, and then the displacement will be used, that is the displacement or the distance we call the the scaled one displacement will be used here, and that will store like 100. That will be calculated, and that ALU result gives the memory. So that we have seen the R2 plus your 100 in the memory, that is memory location, and then it will store in the buffer temporary, the register part. So that is load operations. Memory access means load operations or your store operations will be performed. And note the ALU output is the calculated effective address which we observed in the previous class, previous slide. So then comes to your, the conditional or the control operations. Control operations. In control operations, as we said, it may consist of your jump instructions or your branch instructions, right? The branch instructions. So in the branch instruction, how it is going to be completed, branch instruction means if a unconditional jump is there, we have seen this unconditional jump, then in unconditional jump, you are just having the go to target. Go to target is there. Okay, so two operands will be there. So then first it set the PC program counter for the unconditional jump. Program counter will be set, that will have the effective address, calculated effective address, as we said, go to suppose 99. So the calculated effective address will be there. That effective address will store in the program counter. If it is a conditional jump, then it set the program counter to the calculated effective address. If the condition is met, if the condition is true, then whatever the zero flag value is there, that will be put into your program counter. So that is the if conditional or branch states that we observe in the addressing modes also. And final stage of your instruction execution is your write back. In the write back, it sends the result back to the register file. As we see that, the R2 contain R2 value and R3 value will be given to your ALU, and the result is stored in your R1. Result is stored in your R1 for executing the arithmetic operation like R1 is equal to your R2 plus your R3. So whatever result is there, that is going to store in the R1, that is write back to a register file. Why we are using register file? It is not, sometimes we may write that R15 is equal to R2 plus R3. So result is stored in R15 register. Where this R15 register, these R15 registers are there in general purpose registers, that is having the register file on your CPU, the register file on your CPU, that is having the registers R0, R1, R2, R3, and so on, so up to R15. So that's why, result may go on stored in any of these registers. So it is called your register file. So for that, it is normally it is using the ALU instructions. The ALU output goes and stored in the register. If the load instructions are the memory instructions are the, then from the temporary buffer, it is going to store into the designated registers. So this is a stage for register writing, not the memory writing. Here we all use the registers only, not memory writing. In memory writing, it goes and store into the memory. So putting all stages together in a typical and simple RISC, reduced instruction set computer CPU implementation, or your CISC computers. But nowadays we are using most of the architectures, processors are using the CISC, RISC CPU implementation. So the processor is partitioned into 5 connected stages. So every instruction goes through all these stages, although this instruction does not necessarily trigger the functional units of every stage. So first instruction will be fetched. So IF, it is represented with IF, instruction fetch. Then instruction will be decoded. In the instruction decode, and the register fetching will be happen here. Then the execution, in the execution, if it is ALU operation, directly it will be executed on the accumulator, or if it is a branch or memory operations, then it calculates the effective addresses. And then once it is executed, memory will be allocated, memory allocation will be done, the memory access and branch complete will be happen. And finally, once memory is allocated, the result will go back and write by following the write back. So it is written as IF, means instruction fetching, then the ID for instruction decoding, execution EX will be used for execution representation, and memory will be used for memory allotment, and write back is used for write front back. The result will be write back. So these are the five stages of the instruction execution. We call the 5 stages of your instruction execution. Okay, so this is the implementation overview of your instruction. So what we see in the first part, in the instruction set architecture, first we followed the instruction syntax, instruction design syntax we followed. Okay, in that syntax we followed this the various ways of the instruction design that depends upon the operands, where the operands are. Based on operands, we have seen based on operands. Second, we have seen the addressing modes, the instruction design based on addressing modes. And then we have seen based on your instruction length. Then we categorize these into your CISC and your RISC, and we take the example of your RISC and how these instructions are executed, means in 5 stages. Like first, instructions will be fetched, then the instruction will be decoded, then instruction will be executed, then memory allocation will happen, and finally it will go and the result will be write back. So these are the summary of the instructions in design and classification and the implementation of your instructions. So with this I would like to